the rank of this matrix was only probably only 4, and there was some arbitrary switch for the fourth value. So there's no information really passed here. These other coordinates should not really be used. They're kind of noise values. Okay, so what is what's some other thing I should point out? So in the unnormalized, in the normalized Laplacian layout, I've got all of A, B, C, and D having positive values in the second singular vector, or the second eigenvector. In the unnormalized one, they're all negative. Do you think there's any reason why that is? Okay, so no one's come up with an answer, and that's like good. It's actually the sign of these vectors is basically arbitrary. It happened based on whoever they implemented the eigenvector decomposition inside of Octave or MATLAB. If you chose a different implementation of it, it may have flipped the sign. So this sign is arbitrary. So you're just giving you a sorted order. The ordering, whether it's left to right or right to left, doesn't matter. Right? So you can still split on 0. That would give you the same clusters. You could still scan across them and pick some point. It doesn't matter which order, if they're sorted left to right or if they're sorted right to left. So the sign doesn't matter. Yeah. Okay. So what is the last thing I want to say? So I mentioned that this data was coming from a. Do you have a question?
You said that we have an objective function which was the balance cost of the matrix.
Yeah.
What if we change our objective function and we want to optimize another sort of, I don't know.
Yeah, so there are actually other versions of this. I forget exactly how they go. I think there may be one where it's 1 over Vs times Vt or something like that, and or 1 over the I think it's 1 over the minimum of Vs and Vt instead. And I think there's slightly different versions of the Laplacian that will work better for that formulation of it. There's some derivation which I didn't go through, which I forget if I linked to. Let me see if I linked to a paper. No, I didn't. Got a link to the paper, but there's a paper which really connects this version of the normalized Laplacian to the normalized cut and says why this is a good version to use when you're optimizing it. But you're right, this normalized cut was a little arbitrary how I defined this. And so if you want to use different objective functions, you could still use either of these Laplacians and then look at the sorted order and try and find a good cut, or some other version of the Laplacian. And you can whether one is better than the other is it's not totally clear. There's been a lot of people who've worked with this, and the normalized cut seems to be a pretty popular way to do it. So that's why I mentioned this version. Okay, so one last thing I want to mention is, where does this graph data come from? Right. So one place is like a social network, where I have a graph, I want to find communities in the network. But there could be another interpretation where I start out with some sort of data points, or some sort of, any sort of objects where I have some distance or some similarity function I can define between the elements. And so I don't necessarily have an embedding in 2 dimensions or even some d-dimensional space. Maybe I want to come up with an embedding. Maybe I want to just do clustering based on this similarity function. How can I use this framework for doing that? So instead of using this adjacency matrix where I have a 1 or a 0, I can actually fill in every one of these cells with the similarity value between two objects. So in a very crude similarity, I could say if the distance, so S of A, B is equal to 1 if the distance for some distance I have is less than some threshold and 0 otherwise. Right? So if 2 points are close enough, I can give it a 1, and if they're not close enough, I give it a 0. That fills this in. So this would be one similarity function and one way to fill in this matrix. But if I had something like Jacquard distance, I don't necessarily want to snap it to a 1 or a 0. I can just fill in these spots with the Jacquard distance. Okay? And then I will take out all this 0 self-similarities, and then I can still come up with this degree matrix by summing up the rows and the columns. And I can still then, once I have D and A, I can still write down the Laplacian or the normalized Laplacian. And then I can still do the spectral clustering the same way. I can still lay out my elements in these kind of these 1 or 2 dimensional spaces that kind of spread them out. This gives me a way of embedding my data into, say, a 2-dimensional space so I can visualize it, kind of see how it's laid out. It gives me a way of doing this top-down clustering and all sorts of techniques. So once I have any sort of similarity function, say it's normalized so it's between 0 and 1, I plug it in place of this adjacency matrix, and I do, this same sort of Laplacian, and this gives me clustering and embeddings. So there's a slightly different form of this called, if you have you can use something called multidimensional scaling, and that's basically doing the same thing. It doesn't necessarily go through the same Laplacian transformation. But if you've heard the term multidimensional scaling, it's doing something pretty similar. It starts with, say, an adjacent or some distance matrix between the objects, and it tries to preserve those distances. So that just gives you a way to embed the data into some lower dimensional space. But so this is a very powerful technique. It allows you to do this embedding and this clustering through this kind of idea of thinking of it as a matrix. All right, cool. So next Monday, don't forget to turn in your data collection report, and we'll start on talking about frequent elements and also streaming, which is kind of a large data way of thinking of processing.